Today's aim is let's find rules for dilations in the coordinate plane. All right, when I talk about the coordinate plane, I'm talking about an x and y axis with 4 quadrants. All right, so for 2.1, math talk transforming a point, you're going to mentally find the coordinate of the image of A under each transformation. All right, so I don't want you to do any formal transformations, just in your head, sort of imagine. If you were to translate 0, 0 to 0, 2, that transformation, how would you perform that on A? The second bullet is very similar to that. The third bullet, what would happen if you reflected this point over the x-axis? So mentally try and figure out what that coordinate would be. And then the last one will probably be the most difficult. To rotate this point 180 degrees. I'm not grading this for accuracy. This is just to get you thinking about transformations. So please answer to that on Google Classroom. All right, 2.2, inputs and outputs. All right, this is 1 and 2. I think we've gone over this, a lot, so I don't really feel like dedicating too much time to it. When we see this transformation, x plus 12, y minus 2, we're really talking about a translation of t 12 negative 2, where we take the original x coordinate of the preimage and add 12 to it. And then we also take the original y coordinate of the preimage and subtract 2. So real quick, that'll be 2, 3, 8, 7, and 10, 4. Right, subtracting 2 from all the y's, adding 12 to all the x's. So I guess they have not used this notation yet in this curriculum, but we've been using it a lot, so I'm not going to sketch it and everything. I think we've had enough practice with that. What I would like you to take a look at is number 3 from 2.2. All right, so for each point x, y in the table, find 2 times x, 2 times y. So we're just doubling each coordinate, essentially. So that'll be negative 2, negative 6, negative 2, 2, 10, 2, and 10, negative 6. All right, now they want us to sketch the figure. So now I'd rather you use this blank graph, or if you don't have a printer at home, graph paper, to plot the original and the new coordinates. So I'm just going to stack them here so I can see them both at the same time. And they don't have them labeled, but I will. I'm going to call it A, B, C, D, and A prime, B prime, C prime, and D prime. All right, so let's graph the preimage first. So A is negative 1. Here we go. A is negative 1, negative 3. So I'm going to negative 1 on the x, down 3. All right, that'll be A. B is negative 1, positive 1. C is 5, 1. And D is 5, negative 3. All right, so from just an eye test, this looks like it is a rectangle. Opposite sides are congruent, and opposite sides are parallel. And then we also, that's not so pretty, have right angles. So it's a parallelogram with at least one right angle. That is a rectangle. All right, now I'm going to graph the image. So that'll be with my primes. So negative 2, negative 6, negative 2, negative 6. That'll be A prime, which looks pretty similar to A, or at least placement-wise. B prime is negative 2, positive 2. So that's right where I put that letter B. Let me move that. That is why we write in pencil, folks. B prime. All right, and then C prime is 10, 2. 10,2. Looks like I could probably move C as well. And then D will be 10, -6. D prime, rather. All right, so let's connect those dots. All right, so normally with transformations, at least rigid motions, when I say rigid motions, I mean reflections, translations, or rotations, which take the preimage to an image that is congruent. These two shapes are clearly not congruent. They do look similar, however, but I don't know that for sure. Well, yeah, don't know that for sure. Since it's a quadrilateral, even though they all have the same angles, that's not enough. That's only enough for triangles to prove we're similar. For anything with 4 or more sides, you need to show that the sides are proportional and all the corresponding angles are congruent. So I need to label these sides. So that's 1, 2, 3, 4. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so it looks like that scale factor of 2 is evident, and that makes sense because we multiplied each coordinate by 2. So you would think that we would have a scale factor of 2 there. All right, now let's try this side. 1, 2, 3, 4, 5, 6. And I'm going to guess this is 12. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. So that is a dilation of scale factor 2. So how we write that is actually notated with an uppercase D and then a subscript of 2. However, that's not enough because for any dilation, just like a rotation, we also need to know where its center is. So the way we find that center is to make a straight line with connecting the image and preimage, right? Because we're trying to find our line of projection. And the line of projection is always collinear with the image and preimage. So I'm going to write that down because that's important. Line of projection is collinear with image and preimage. All right, so let's see if we can find that. So already I can see when I line these up that it goes right through the origin. So, I mean, I'm going to guess as the origin just for neatness sake, but it could theoretically be any point on this line. All right, so that hits the origin. Sorry, that wasn't a perfect line. All right, there we go. All right, if we look at this, the slope is the same, right? Up 3 over 1, up 3 over 1, and that brings me right to the origin, so I know I've done that correctly. So let's see if the other points also have that same center of dilation. And it looks like they do. All right, so where they intersect has to be the center of dilation since it has to be the same for all 4 coordinates. There we go. So I can say this is a dilation scale factor 2 centered at the origin. All right, so normally when we don't specify the center, you can sort of assume it's the origin, but anytime you talk about one, especially in my class, you need to state it. All right, so yeah, we got the dense transformation. That's what they asked about in the second part here. All right.